Tonight, we embark on a journey that will reshape your understanding of where you stand in the vast expanse of space. We are going to uncover just how remarkably small our planet Earth truly is. This is not simply about measuring our world against the Sun or comparing it to Jupiter. We are talking about the genuine scale, the perspective that causes Earth to become nearly invisible. Because there is something most people never fully grasp. Earth is not merely small, it is so astonishingly minute that finding adequate language to capture its tininess becomes nearly impossible. This journey will take us from the familiar ground beneath your feet to the very edge of the observable universe. We will move outward in stages, each one revealing a new layer of cosmic reality. At each stage, we will pause to let the implications settle. We will give ourselves time to adjust to each new perspective before moving further. Because understanding the true scale of the universe is not just an intellectual exercise. It changes something fundamental about how you see yourself and your place in existence. Think of this exploration as peeling away layers of perspective. Each layer reveals something new, something larger, something that makes the previous layer seem small in comparison. We will start with what we can see and touch, the solid ground of Earth. Then we will step back, again and again, each time gaining a wider view. And with each step back, Earth will shrink a little more, until finally it becomes so small that we struggle to comprehend its tinniness. By the time we reach the end of this exploration, you will perceive our planet and your own existence through an entirely transformed lens. Before we venture deeper, if you appreciate these journeys through space and these reflections on our place in the cosmos, a simple like or subscription would genuinely support this channel's growth. It may seem like a modest action, but it creates meaningful impact. Now, let us begin this voyage of discovery. Let us start with Earth itself, the world we call home, the planet beneath our feet each day. From our vantage point here on the surface, Earth appears immense. You could dedicate your entire lifetime to exploration and still leave countless corners unseen. The continents extend for thousands upon thousands of miles. The oceans blanket approximately 71% of the surface. Mount Everest climbs nearly 30,000 feet toward the heavens. Think about your own experience of Earth's size. If you have ever taken a long road trip, you know how vast a single country can seem. Driving across the United States from coast to coast takes several days of continuous travel. Flying across the Pacific Ocean requires many hours in an aircraft moving at hundreds of miles per hour. These experiences give us a direct, visceral sense of Earth's enormousness. The diversity of landscapes on Earth itself speaks to the planet's vastness. From the frozen expanses of Antarctica to the scorching deserts of the Sahara, from the dense rainforests of the Amazon to the towering peaks of the Himalayas, Earth presents an incredible variety of environments. Each ecosystem contains its own web of life, its own climate patterns, its own geological features. A person could spend years studying a single mountain range or a single coral reef and never exhaust its complexity. Earth rotates on its axis once every 24 hours, creating the cycle of day and night that governs life on the surface. This rotation also creates the Coriolis effect, which influences weather patterns, ocean currents, and the swirling motion of hurricanes. The planet's magnetic field, generated by movement of molten iron in its core, extends far into space, creating a protective bubble called the magnetosphere that shields us from harmful solar radiation and cosmic rays. Without this magnetic shield, Earth's atmosphere would have been stripped away by the solar wind billions of years ago. Mars lost most of its atmosphere in this way, after its magnetic field weakened and eventually disappeared. Earth's magnetic field also creates the beautiful auroras, the northern and southern lights, when charged particles from the Sun interact with gases in our upper atmosphere. Consider the depth of Earth's oceans. The deepest point, the Challenger Deep in the Mariana Trench, plunges nearly 7 miles below the surface. If you placed Mount Everest at the bottom of this trench, its peak would still sit more than a mile underwater. The ocean depths remain largely unexplored. We have mapped the surface of Mars in greater detail than we have mapped our own ocean floors. The pressure at these depths reaches over 8 tons per square inch. The darkness is absolute. Yet life thrives even there in forms adapted to conditions that would crush and freeze most surface organisms. Earth's atmosphere extends hundreds of miles above the surface, though most of the air we breathe exists in the lowest layer, the troposphere, which reaches only about 7 miles high. Above that lies the stratosphere, where the ozone layer shields us from harmful ultraviolet radiation. Higher still, the mesosphere, thermosphere, and exosphere gradually transition into the vacuum of space. There is no sharp boundary where atmosphere ends and space begins, only a gradual thinning until molecules become so rare that we call it empty. To the earliest humans, Earth represented everything that existed. It was the entirety of the universe. The sky overhead seemed like nothing more than a dome decorated with lights. The ground below appeared flat and continued endlessly in every direction. This understanding made perfect sense given what they could observe. When you gaze toward the horizon, Earth truly does appear flat. The curvature remains too subtle for the human eye to detect without ascending to great heights. Ancient civilizations built entire cosmologies around this Earth-centered view. The Babylonians imagined Earth as a flat disk floating on an infinite ocean. The ancient Hindus envisioned Earth resting on the backs of elephants standing on a giant turtle. These models attempted to explain what people saw around them. They were reasonable conclusions based on limited perspective. The realization that Earth was round came gradually. Greek philosophers like Pythagoras and Aristotle argued for a spherical Earth based on observations. They noticed that ships disappeared hull first over the horizon. They observed Earth's round shadow on the moon during lunar eclipses. They saw different constellations visible from different latitudes. These clues suggested Earth was not flat, but curved. Eratosthenes, a Greek mathematician and geographer, actually calculated Earth's circumference with remarkable accuracy around 240 BC. He noticed that at noon on the summer solstice in the city of Syene, the sun shone directly down a well, casting no shadow. But at the same time in Alexandria, about 500 miles north, vertical objects cast shadows. By measuring the angle of the shadow and knowing the distance between the cities, he calculated Earth's circumference to within a few percent of the true value. This achievement, accomplished over 2,000 years ago with simple geometry, demonstrates the power of careful observation and logical reasoning. Earth measures roughly 7,926 miles in diameter at its widest point, the equator. If you decided to walk completely around the equator and somehow possessed the ability to walk across water, you would traverse approximately 25,000 miles. Maintaining a steady walking pace of 3 miles per hour and walking 8 hours each day, this journey would consume about 3 years and 1 month of your life. That represents a genuinely long walk. To put this in another context, if you could drive around the equator at highway speed, maintaining 60 miles per hour without stopping, it would still take you over 17 days of continuous driving. That is more than 2 weeks of non-stop travel just to circle our planet once. The Wright brothers' first flight in 1903 covered only 120 feet. At that rate, it would take them over 1 million flights to circle Earth. From a human perspective, Earth is authentically large. The surface area of our planet encompasses roughly 197 million square miles. To help frame this enormous magnitude, imagine you wanted to visit every single square mile. If you spent merely 1 second in each location, this endeavor would require over 6 years of continuous, uninterrupted travel. But consider this from another angle. If you tried to count every square mile of Earth's surface, counting 1 per second without pause for sleep or rest, you would spend over 6 years just counting. And in that time, you would not see any of those places, experience any of their landscapes, or understand anything about them. You would simply be acknowledging their existence. The actual exploration would take lifetimes upon lifetimes. The United States, recognized as one of the largest countries on Earth, covers only about 3.8 million square miles. That amounts to less than 2% of Earth's total surface area. Russia, the largest country, covers about 6.6 million square miles. That is still only about 3% of Earth's surface. The Pacific Ocean alone covers approximately 63 million square miles, nearly 1/3 of Earth's total surface. Think about the sheer volume of water in Earth's oceans. The total volume of all ocean water is approximately 326 million cubic miles. If you could gather all that water into a single sphere, it would measure about 860 miles in diameter. That sphere would be enormous by human standards, yet it would represent only a tiny fraction of Earth's total volume. Most of Earth consists of rock and metal, the solid layers beneath our feet. But here is where our perspective begins to transform. When you zoom out, even slightly, when you begin placing Earth alongside other objects drifting through space, our planet starts to shrink. Not physically shrinking, of course, but diminishing in its apparent significance. Earth stops being everything. It becomes simply one object among countless others. And as we continue zooming outward, it grows smaller and smaller until it transforms into something almost impossible to perceive with the naked eye. This transformation of perspective happens gradually. We do not notice it at first. Earth still dominates our view for a while. But with each step outward, with each new comparison, something shifts. The planet that seemed so vast begins to look smaller. The distances that seemed so enormous begin to look trivial. And we are just beginning this journey. Our first destination on this cosmic journey brings us to our nearest celestial neighbour. The Moon follows its orbital path around Earth at an average distance of approximately 200 to 38,855 miles. That is roughly equivalent to the distance you would travel if you circled Earth's equator 9.5 times. It seems far, and by human standards, it truly is far. To understand this distance better, imagine you could build a highway to the Moon. Driving at 60 miles per hour without stopping, you would need approximately 165 days to reach it. That is more than 5 months of continuous driving. And remember, you would be traveling through perfect vacuum, through the hostile environment of space, across a distance that contains absolutely nothing except occasional particles of dust. When the Apollo astronauts journeyed to the Moon, their voyage required about 3 days to complete. The Moon itself possesses a diameter of approximately 2,159 miles. That measures out to roughly 27% of Earth's diameter. So the Moon is certainly smaller than Earth, but the difference is not dramatic. If Earth were the size of a basketball, the Moon would measure about the size of a tennis ball. The Moon is actually quite large compared to other moons in the solar system. Most planetary satellites are tiny compared to their parent worlds. Mars's moons, Phobos and Deimos, are only a few miles across. Many of Jupiter's moons are smaller than our cities, but Earth's moon is substantial. It represents a significant fraction of Earth's size. Scientists believe the Moon formed about 4.5 billion years ago, shortly after Earth itself coalesced. The leading theory suggests that a Mars-sized object, sometimes called Theia, collided with the young Earth. This catastrophic impact ejected enormous amounts of debris into orbit. Over time, this debris came together to form the Moon. This violent origin story means the Moon is actually made partially from Earth itself, sharing much of the same composition. The Moon's surface tells the story of billions of years of cosmic bombardment. The dark areas we see, called maria, are ancient lava plains that formed when asteroid impacts melted the lunar crust. The lighter highlands are older, more heavily cratered regions. Without atmosphere or geological activity to erase them, these craters preserve a record of impacts stretching back billions of years. But here comes the interesting part. The distance separating Earth and the Moon spans roughly 30 times Earth's diameter. Picture placing 30 planet Earths in a single line stretching between us and the Moon. That illustrates the tremendous amount of empty space existing in that gap. This empty space is not merely empty in the sense of being devoid of air. It is empty in a more profound way. There are no landmarks, no reference points, nothing to see or experience for hundreds of thousands of miles. Just blackness and vacuum and distance. The astronauts who traveled to the Moon spent days in this void, suspended between two worlds, experiencing a loneliness and isolation unlike anything possible on Earth. During their journey, the astronauts reached a point where Earth and the Moon appeared roughly the same size in their windows. This occurred about 200,000 miles from Earth. At that point, they had left Earth's gravitational sphere of influence and entered the Moon's. They were no longer falling toward Earth, but falling toward the Moon. This crossing represented a profound moment, a transition from one world's domain to another's. Most people remain unaware of this reality. When you encounter pictures showing Earth and the Moon together, they are typically depicted much closer than their actual separation. The truth reveals a vast amount of nothingness stretching between us and our closest cosmic companion. This becomes our first clue that space consists mostly of emptiness. Even within our immediate cosmic neighborhood, the distances prove enormous when compared to the actual sizes of the objects themselves. If you made an accurate scale model of the Earth and Moon system on a piece of paper, with Earth the size of a quarter, the Moon would be a smaller coin positioned about 20 feet away. Most illustrations compress this distance to fit the page, creating a misleading impression of how close these bodies actually are. The Moon's relationship with Earth stands out as quite unique within our solar system. Most moons appear tiny when compared to their parent planets, but our Moon is relatively large in proportion to Earth. In truth, the Earth and Moon system sometimes receives the name double planet because the Moon possesses such substantial size relative to Earth. The Moon's mass creates real, tangible effects on our planet. It generates the tides we observe every day. The Moon also helps stabilize the tilt of Earth's axis. Without our Moon's gravitational influence, Earth's axis might wobble dramatically across vast periods of time, triggering extreme climate variations that could render complex life forms difficult or perhaps impossible to sustain. The tides themselves represent a visible demonstration of gravitational forces acting across space. The Moon's gravity pulls on Earth's oceans, creating bulges on the sides facing toward and away from the Moon. As Earth rotates beneath these bulges, we experience high and low tides. The Sun also contributes to tides, though less strongly due to its greater distance. These tidal forces have shaped life on Earth in fundamental ways. Tidal pools create unique ecosystems. Tidal rhythms influence the behavior of countless marine species. Some scientists suggest that tides may have played a role in life's transition from sea to land billions of years ago. The moon also affects Earth in ways less immediately visible. The tidal forces that create ocean tides also create friction, which gradually slows Earth's rotation. Billions of years ago, days were shorter. In the distant future, if Earth and the moon still exist, Earth will become tidally locked to the moon, always showing the same face to it, just as the moon currently shows the same face to Earth. This tidal locking already affects the moon. The same hemisphere of the moon always faces Earth. The far side, often incorrectly called the dark side, remains hidden from our view. It was not photographed until spacecraft orbited the moon in the late 1960s. The far side looks quite different from the near side, with more highlands and fewer of the dark Maria plains. When you look at the moon from Earth's surface, it appears roughly the same size in the sky as our sun. This represents a complete coincidence, one of the remarkable accidents of our solar system. The sun measures about 400 times larger than the moon, but it also sits about 400 times farther away from us. This numerical coincidence provides us with total solar eclipses, those rare moments when the moon perfectly covers the face of the sun. During a total solar eclipse, the moon's shadow races across Earth's surface at over 1,000 miles per hour. Within the path of totality, day becomes night for a few precious minutes. Stars appear in the daytime sky, the temperature drops, birds stop singing, confused by the sudden darkness. And the sun's corona, its outer atmosphere normally invisible in the sun's glare, becomes visible as a delicate halo around the moon's silhouette. These eclipses will not last forever. The moon is also slowly drifting away from Earth. Each passing year, it moves approximately 1.5 inches farther into space. This gradual departure happens because of tidal interactions between the two bodies. Billions of years ago, the moon orbited much closer to Earth, and a single day on our planet lasted much shorter, perhaps only 5 hours in length. In the distant future, perhaps 1 billion years from now, the moon will have moved far enough away that it will no longer completely cover the sun during eclipses. Future observers will see annular eclipses, where a ring of sunlight remains visible around the moon's edge, and eventually the moon will recede far enough that total solar eclipses will no longer occur at all from Earth's surface. Those future inhabitants of Earth will have lost one of the cosmic spectacles we can still witness today. For now, the moon remains our closest companion in the vast emptiness of space. And in 1969, humans walked upon its surface for the very first time. A historic moment that demonstrated what our species becomes capable of when we push against the boundaries of exploration and discovery. The Apollo missions represent one of humanity's greatest achievements. 12 humans walked on the moon between 1969 and 1972. They collected samples, conducted experiments, planted flags, and looked back at Earth hanging in the black sky. The famous Earthrise photograph, showing our blue planet rising above the moon's grey horizon, gave humanity a new perspective on our world. We saw Earth as a whole, a single fragile sphere in the darkness, for the first time. The astronauts who stood on the moon described Earth as looking like a beautiful marble suspended in the void. From that distance, all the conflicts, all the divisions, all the borders that seem so important down here become invisible. You cannot see nations from the moon. You cannot see wars or politics. You see only one world, blue and white and brown, a haven of life in an otherwise lifeless void. Now, let us turn our attention to the sun. The sun serves as the reason we exist at all. Without its continuous light and heat, Earth would be nothing more than a frozen rock tumbling through the darkness of space. But the Sun also represents the point where Earth's dimensions truly begin to fade in comparison. The Sun has a diameter measuring about 864,000 miles. That makes it 109 times larger than Earth's diameter. The Sun's volume proves so immense that approximately 1.3 million Earth-sized worlds could fit within the same space. Consider that statement for a moment. Every mountain range, every ocean, every city, every single person who has ever drawn breath, all of human history unfolded on a planet whose volume represents less than 1/1,000,000th of the Sun's interior. Imagine you could hollow out the Sun and start filling it with Earths. You would need to add 1.3 million planets the size of ours just to fill the space. If you added 1 Earth per second, this process would take about 15 days of continuous work. And at the end, you would have replicated our entire world more than 1,000,000 times over, each one fitting comfortably inside the Sun. The Sun contains 99.86% of all the mass present in our solar system. Everything else, including all the planets, all the moons, all the asteroids, and all the comets combined, accounts for only 0.14%. The Sun also sits about 93 million miles away from Earth. Astronomers call this distance 1 astronomical unit, often abbreviated as AU. However, we should say 1 astronomical unit in full. This dominance of the Sun in our solar system cannot be overstated. Jupiter, the largest planet, contains most of the remaining mass in the solar system. But even Jupiter represents only about 1,000th of the Sun's mass. All the other planets combined amount to less than half of Jupiter's mass. The Sun is not just the largest object in the solar system, it is the solar system, in terms of where the mass resides. Light departing from the Sun requires about 8 minutes and 20 seconds to reach our planet. If the Sun suddenly vanished from existence, we would not know for more than 8 minutes, because the light informing us of its disappearance would still be travelling toward us through space. This creates a strange temporal disconnect. When you look at the Sun, you are seeing it as it was over 8 minutes ago. You are looking into the past. If something dramatic happened on the Sun right now, you would not know until more than 8 minutes from now. In a sense, we never see the Sun as it currently exists. We always see its history. This delay, this light travel time, becomes a fundamental aspect of observing the universe. Everything we see in the night sky is ancient light. The moon we see is about 1 second in the past. The planets we observe are minutes or hours in the past. The nearest stars are years in the past. Distant galaxies show us light that began its journey millions or billions of years ago. We do not observe the universe as it is, we observe the universe as it was. This means that astronomy is also a form of time travel. When we look at distant objects, we are literally seeing them as they existed in the past. The farther away something is, the further back in time we see it. A telescope becomes a time machine, allowing us to peer into the history of the cosmos. To truly grasp this distance, consider that a vehicle maintaining typical highway speeds would need 176 years to cross this 93 million mile gulf. The fastest spacecraft humans have ever constructed, the Parker Solar Probe, still needs months to approach the Sun, despite travelling at speeds exceeding 400,000 miles per hour at its closest approach. The Parker Solar Probe, launched in 2018, is designed to study the Sun's outer atmosphere by passing through the corona. At its closest approach, it endures temperatures of about 2,500 degrees Fahrenheit. Its heat shield, made of carbon composite foam, protects the instruments behind it. The probe travels faster than any human-made object in history. using gravity assists from Venus to gradually spiral closer to the Sun. The Sun is actually a fairly ordinary star in cosmic terms. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It has existed for about 4.6 billion years, making it roughly middle-aged in stellar terms. It possesses enough nuclear fuel to continue burning for another 5 billion years or so before it begins its dying process. In about 5 billion years, the Sun will exhaust its hydrogen fuel in the core. It will then expand into a red giant, swelling until it potentially engulfs Mercury and Venus. Earth may survive this expansion, but our planet's oceans will boil away and the surface will become molten. Eventually, the Sun will shed its outer layers, creating a beautiful planetary nebula. The core will collapse into a white dwarf, a dense remnant about the size of Earth, but containing over half the Sun's current mass. This white dwarf will slowly cool over trillions of years, eventually becoming a cold, dark cinder. The Sun's power output is absolutely staggering. Every single second, it converts about 600 million tons of hydrogen into helium through the process of nuclear fusion. This transformation releases an enormous quantity of energy. The Sun generates more energy in 1 second than all of human civilization has produced throughout its entire existence. To put this in perspective, human civilization currently uses about 20 trillion watts of power. That includes all electricity, all fuel for vehicles, all heating and cooling, everything. The Sun produces about 384 trillion watts. That is about 19 billion trillion times more power than human civilization uses. In 1 second, the Sun produces enough energy to power human civilization at current levels for about 500,000 years. The surface of the Sun maintains a temperature of about 10,000 degrees Fahrenheit. The core, where fusion reactions occur, reaches approximately 27 million degrees Fahrenheit. The pressure at the core measures about 260 billion times Earth's atmospheric pressure at sea level. These conditions are so extreme that matter behaves in ways impossible to replicate on Earth. In the core, hydrogen nuclei move so fast and collide so forcefully that they overcome their electrical repulsion and fuse together. This process, nuclear fusion, converts mass directly into energy, according to Einstein's famous equation. About 4 million tons of mass disappear every second in the Sun, converted entirely into energy. Scientists have spent decades trying to replicate fusion on Earth as a potential energy source. If successful, fusion power could provide virtually limitless clean energy. But achieving the conditions necessary for sustained fusion has proven extraordinarily difficult. The Sun manages this feat naturally through its immense mass and gravity. Creating those same conditions in a laboratory or power plant requires sophisticated technology that we are still developing. The Sun possesses a complex internal structure. The core, where fusion occurs, occupies only about 2% of the Sun's volume, but contains nearly half its mass. Surrounding the core is the radiative zone, where energy slowly works its way outward through countless absorptions and re-emissions of photons. A single photon can take hundreds of thousands of years to travel from the core to the surface, bouncing randomly between atoms in a drunkard's walk toward freedom. Beyond the radiative zone lies the convective zone, where hot plasma rises, cools, and sinks in vast churning cells. The visible surface, the photosphere, is where the Sun's light finally escapes into space. Above that, the chromosphere and corona extend millions of miles, creating the Sun's outer atmosphere. These outer layers are paradoxically hotter than the surface, a mystery that scientists are still working to fully understand. The Sun also produces solar flares and coronal mass ejections. These represent enormous releases of energy and matter from the Sun's outer atmosphere. When these eruptions direct themselves toward Earth, they can create beautiful auroras dancing near the polar regions. But they can also disrupt satellite operations, power grids, and communication systems. The most powerful solar flares release as much energy as billions of megatons of TNT exploding simultaneously. In 1859, a massive solar storm called the Carrington Event struck Earth. Telegraph systems worldwide failed. Some telegraph operators reported receiving electric shocks. Auroras appeared as far south as the Caribbean. If a similar event occurred today, it could cause trillions of dollars in damage to our technology-dependent civilization. Observing the Sun reminds us that Earth does not occupy the center of our solar system. For the majority of human history, people believed Earth sat at the center of everything. It required brilliant thinkers like Nicolaus Copernicus and Galileo Galilei to demonstrate that the Sun actually occupied the center and that Earth orbited around it. This revelation served as humanity's first major lesson in cosmic humility. The shift from geocentrism to heliocentrism represented more than just a correction of astronomical facts. It fundamentally changed humanity's understanding of our place in the cosmos. We were not at the center. We were not special in location. We were one planet among several, orbiting an ordinary star. This realization challenged religious and philosophical assumptions that had stood for thousands of years. Galileo faced persecution for supporting the heliocentric model. He was tried by the Roman Inquisition and spent the last years of his life under house arrest, but the truth could not be suppressed forever. More observations confirmed the heliocentric model. Planetary motions made sense. Predictions became accurate. Eventually, the evidence became overwhelming, and the Earth-centered universe gave way to reality. Now, let us broaden our view beyond the Sun to consider the other planets sharing our solar system. Mercury, the closest planet to the Sun, has a diameter of about 3,000 miles. It orbits the Sun at an average distance of 36 million miles. Venus measures roughly 7,500 miles across and sits about 67 million miles from the Sun. Mercury's proximity to the Sun creates extreme conditions. Surface temperatures range from about 800 degrees Fahrenheit on the day side to minus 290 degrees on the night side. Mercury rotates slowly, taking about 59 Earth days to complete one rotation, but it orbits the Sun in only 88 Earth days. This creates a strange situation where a single day on Mercury, from sunrise to sunrise, actually lasts about 176 Earth days, or 2 Mercurian years. Venus, often called Earth's twin due to its similar size, presents a cautionary tale. Its thick atmosphere, composed mostly of carbon dioxide, creates a runaway greenhouse effect. Surface temperatures reach about 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure at the surface equals about 90 times Earth's, equivalent to being 1 kilometer underwater in Earth's oceans. Clouds of sulfuric acid fill the atmosphere, raining down but evaporating before reaching the surface. Venus rotates in the opposite direction from most planets, spinning slowly backward. A day on Venus, from sunrise to sunrise, actually lasts longer than a Venusian year. The planet may have once had oceans and more Earth-like conditions, but the greenhouse effect spiraled out of control, boiling away any water and creating the hellish world we see today. Mars, the next planet beyond Earth, has a diameter of about 4,200 miles and orbits at approximately 142 million miles from the Sun. But the truly giant planets lie farther out. Jupiter, the largest planet in our solar system, possesses a diameter of roughly 86,800 miles. That makes it 11 times wider than Earth. Mars has captured human imagination for centuries. Its reddish appearance in the night sky, caused by iron oxide on its surface, earned it the name of the Roman god of war. In the late 19th and early 20th centuries, some astronomers believed they saw canals on Mars, leading to speculation about Martian civilizations. We now know these canals were optical illusions. But the question of life on Mars remains open. Mars once had liquid water on its surface. Ancient river valleys and lake beds mark its landscape. Today, Mars is cold and dry, with a thin atmosphere composed mostly of carbon dioxide. But underground ice exists, and possibly underground liquid water. The possibility of past or present microbial life on Mars makes it one of the most interesting targets for exploration. Mars has two small moons, Phobos and Deimos, both likely captured asteroids. Phobos orbits so close to Mars that tidal forces are slowly pulling it closer. In about 50 million years, it will either crash into Mars or break apart to form a ring around the planet. From the Martian surface, Phobos appears to rise in the west and set in the east, moving across the sky in only 4 hours. Jupiter's volume could contain about 1,300 Earths. The Great Red Spot on Jupiter, a massive storm system that has raged for centuries, is larger than Earth itself. Saturn, famous for its spectacular ring system, measures about 72,000 miles in diameter. That is 9 times Earth's diameter. Uranus spans roughly 31,000 miles across, and Neptune measures about 30,000 miles in diameter. Jupiter is not just large, it is a world unto itself. It has at least 79 moons, including 4 large ones discovered by Galileo in 1610. These Galilean moons, Io, Europa, Ganymede, and Callisto, are each unique worlds. Io is the most volcanically active body in the solar system. Europa has a global ocean beneath its icy crust, possibly containing more water than all of Earth's oceans combined. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. Callisto is heavily cratered, preserving a record of ancient impacts. Saturn's rings are made of countless ice particles and rocks, ranging in size from grains of sand to mountains. These rings stretch for hundreds of thousands of miles, but are surprisingly thin, in some places only about 30 feet thick. The origin of Saturn's rings remains debated. They may be remnants of a shattered moon or leftover material from Saturn's formation. Saturn also has at least 82 moons. Titan, its largest moon, has a thick atmosphere and lakes of liquid methane and ethane on its surface. Titan is larger than the planet Mercury and is the only moon in the solar system with a substantial atmosphere. Its atmosphere is actually thicker than Earth's. The surface temperature on Titan hovers around -290 degrees Fahrenheit. At these temperatures, water ice is as hard as rock, and methane exists as a liquid. Titan has a weather cycle involving methane rain, methane rivers, and methane lakes. It is one of the most Earth-like bodies in the solar system, despite being utterly alien. Uranus and Neptune, the ice giants, orbit in the cold outer solar system. Uranus has an unusual characteristic. Its axis of rotation is tilted on its side, possibly due to a massive collision early in its history. This means Uranus essentially rolls around the Sun, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Neptune, the most distant planet, has the strongest winds in the solar system, with speeds reaching over 1,000 miles per hour. Even with these massive outer planets, they all pale in comparison to the Sun. Jupiter, the giant among planets, still measures only about 1/10 the diameter of the Sun. If the Sun were hollow, you could fit about 1,000 Jupiters inside it. This comparison illustrates how the Sun dominates the solar system, not just in mass, but in volume. The planets, for all their diversity and complexity, are tiny compared to the star they orbit. And Earth is tiny even compared to the largest planets. The distances between these planets prove equally impressive. Jupiter orbits at about 484 million miles from the Sun. Saturn sits approximately 886 million miles out. Uranus orbits at roughly 1.8 billion miles from the Sun. Neptune, the most distant major planet, follows its path at about 2.8 billion miles from the Sun. These distances create enormous gulfs of empty space. If you built a scale model where Earth was the size of a marble, the Sun would be about 8 feet in diameter, and you would need to place it about 1,000 feet away. Jupiter would be nearly a mile away from the Sun in this model. Neptune would sit more than 5 miles away. In such a model, the solar system would be mostly empty space. You would walk for miles between planets, seeing nothing but emptiness. This emptiness characterizes space. Objects, even large ones, are rare. Void is common. Most of the universe consists of nothing at all. The solar system also contains countless smaller objects. The asteroid belt between Mars and Jupiter holds millions of rocky bodies. Some asteroids measure hundreds of miles across, while others are no larger than pebbles. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies. Pluto, once considered the 9th planet, resides in this distant realm. Pluto has a diameter of only about 1,400 miles, making it smaller than Earth's moon. The asteroid belt is not densely packed like it appears in movies. The average distance between asteroids in the belt is about 600,000 miles. If you were standing on one asteroid, you probably could not see another one without a telescope. Spacecraft pass through the asteroid belt regularly without any danger of collision. Pluto, discovered in 1930, was considered the 9th planet for 76 years. In 2006, astronomers reclassified it as a dwarf planet, partly because many other similar-sized objects were being discovered in the Kuiper Belt. Pluto has 5 known moons. Its largest moon, Charon, is so large relative to Pluto that the two bodies orbit a common point between them, forming a binary system. The New Horizons spacecraft flew past Pluto in 2015, giving us our first close-up views of this distant world. The images revealed a surprisingly complex surface, with mountains made of water ice, vast plains of frozen nitrogen, and a thin atmosphere that escapes into space. Pluto turned out to be far more interesting and geologically active than anyone expected. Even farther out, past the Kuiper Belt, extends the Oort cloud. This theoretical sphere of icy objects surrounds the entire solar system at distances of up to 100,000 astronomical units from the Sun. That places the outer edge of the Oort cloud about 1.9 light-years away. A light-year represents the distance light travels in 1 year, approximately 5.9 trillion miles. The Oort cloud has never been directly observed because the objects within it are too small and too far away to see with current telescopes. But we infer its existence from long-period comets, those comets that take hundreds or thousands of years to orbit the Sun. These comets appear to come from a spherical cloud surrounding the solar system. The Oort cloud may contain trillions of icy bodies. Every so often, the gravity of a passing star or the galaxy itself disturbs one of these objects, sending it falling toward the inner solar system. As it approaches the Sun, the ice heats up and forms a glowing coma and tail, creating the spectacular comets we occasionally see in our skies. At this scale, our solar system begins to seem vast. But now we must confront a realization that feels almost unsettling. Even at the edge of our solar system, even after passing the outer planets and drifting beyond the Kuiper Belt, we are still unimaginably close to home in cosmic terms. The distances that felt limitless only moments ago will soon collapse into almost nothing as our perspective shifts again. Beyond the gravitational influence of the Sun lies interstellar space. This is the realm between stars, where matter becomes so sparse that a cubic centimeter of space may contain only a handful of atoms drifting silently through the void. Here, the warmth of the Sun fades into the deep cold of space, where temperatures approach just a few degrees above absolute zero. There is no sound, no wind, no sense of motion. Only darkness, distance, and time. If you could drift here without a body, without need for air or warmth, you would experience something that defies all earthly comparison. There would be no horizon, no up or down, no day or night. Stars would surround you in every direction, fixed points of distant fire suspended in endless black. And yet, despite their brilliance, they would feel impossibly far away, unreachable, isolated from one another by gulfs of emptiness so vast they silence the imagination. The nearest star now lies so far that even light itself struggles to make the crossing in any human sense of time. A single beam departing from our Sun takes more than 4 years to reach the nearest neighbouring star. 4 years of uninterrupted travel at the fastest speed permitted by nature, a beam of light, restless and tireless, racing outward through nothingness for 4 entire years before it brushes the surface of another sun. For anything slower than light, the journey becomes not just long, but absurdly long. A spacecraft travelling faster than any humans have ever built would still require tens of thousands of years to reach even the closest star. Generations would rise and fall. Entire civilizations would bloom and vanish, while the vessel drifted silently through darkness, inching forward across an ocean, measured not in miles, but in light years. And this is where the scale of emptiness truly begins to dominate the story of the universe. Space is not filled with stars and galaxies the way the night sky might suggest. Space is emptiness first. Stars are rare interruptions in a vast, nearly perfect vacuum. The universe is mostly nothing. Almost all of its volume contains no planets, no suns, no life. Just darkness and a few wandering particles, passing one another without ever meeting. Between stars, entire solar systems could pass without ever coming close. If the sun were reduced to the size of a grain of sand, the nearest star would lie kilometers away. And between those 2 grains of cosmic dust would stretch pure nothingness. No planets, no light, no warmth, only cold, silent, uninterrupted space. This emptiness plays a profound role in shaping the universe. It governs how galaxies form and evolve. It stretches the light of distant stars. It ensures that civilizations, if they arise elsewhere, remain forever separated by distances that may never be crossed. The universe is not just large, it is spacious beyond any meaning the human mind can comfortably hold. And yet, from within this emptiness, structures still emerge. As we move outward from our dying warmth, we find that stars do not wander alone. They gather into enormous families called galaxies. Each galaxy is a vast island of matter adrift in the cosmic sea. Billions of stars bound together by gravity, rotating slowly around an unseen center. From a distance, galaxies resemble glowing whirlpools suspended in darkness, their spiral arms stretching outward like luminous currents frozen in time. Inside a galaxy, stars are born. Clouds of gas collapse under their own weight, heating, compressing, igniting into new suns. Around some of them, planets form. On rare worlds, chemistry organizes itself into life. And on at least one such world, consciousness has emerged, trying to understand the ocean from which it rose. But galaxies themselves are separated by unimaginable distances. Even within the grand architecture of the universe, these immense structures remain mostly alone. The space between galaxies dwarfs even the space between stars. Light can spend millions of years drifting between one galaxy and the next, carrying messages from ancient times to observers that did not yet exist when the light first began its journey. From this perspective, every galaxy becomes its own universe of motion and memory. Civilizations may rise and fall within them without ever knowing that others exist elsewhere. The night skies of alien worlds may look just as quiet and lonely as ours once did, unaware of the vast communities of galaxies scattered beyond their visibility. As we drift farther outward, even galaxies begin to cluster together. Gravity, patient and relentless, gathers them into groups, into clusters, into immense rivers of matter, stretching across hundreds of millions of light years. These structures form the scaffolding of the universe, great cosmic filaments threading through the darkness, carrying galaxies along invisible gravitational highways. Between these filaments lie voids, true voids, regions so empty that even galaxies rarely intrude. They span distances larger than many galaxy clusters themselves, expanding like silent bubbles in the cosmic web. If you could stand at the center of one of these voids, you might see almost nothing in any direction for tens or hundreds of millions of light years. The universe would appear nearly abandoned, a place where existence itself seems absent. And yet, even here, space is not truly empty. Invisible matter still drifts through the void. Dark matter, unseen but deeply powerful, shapes the architecture of everything we observe. It does not shine, does not reflect, does not absorb light, and yet its gravity bends the paths of galaxies and sculpts the cosmic web itself. Without it, the large-scale universe as we know it could not exist. The deeper we go, the more the universe reveals that what we can see is only a fraction of what is truly there. The stars, the galaxies, the glowing structures that fill our images are merely the visible traces of an unseen framework that holds everything together. And beyond even this vast network of matter and voids lies a horizon, a boundary not of space, but of time. There exists a distance beyond which light has simply not had enough time to reach us since the universe began. No matter how powerful our telescopes become, no matter how advanced our instruments grow, we will never see beyond this limit. Not because nothing exists there, but because the messages from that region are still in transit through the expanding fabric of space. This horizon surrounds us in every direction. It forms a sphere of visibility centered on our position in the universe, defining everything we will ever be able to observe directly. All the galaxies we study, all the cosmic structures we map, all the ancient light we analyze, all of it exists within this finite window. Beyond it, the universe continues, but it remains forever hidden. At this boundary, space itself glows faintly with the afterimage of creation. The oldest light we can observe does not come from stars or galaxies, but from the universe itself when it was young, hot, and dense. This ancient radiation fills all directions evenly, a gentle whisper of the moment when matter and light first parted ways. It is the echo of the beginning. And this brings us to one of the most difficult truths of all. The universe has not only immense size, it also has immense age. Time itself stretches to scales that dwarf all human history. The universe existed long before the first cell formed on Earth. It will continue long after the last star burns out. Civilizations, if they arise, flicker through this grand timeline like sparks in a storm. Stars live for millions, billions, even trillions of years depending on their size. Some burn fast and die young. Others glow quietly for longer than the current age of the universe. Galaxies collide, merge, evolve, and transform over eons so vast that no biological memory could ever span them. Even the universe itself appears to have a slow, distant destiny. As space continues to expand, galaxies will drift farther apart. Distant clusters will slide beyond one another's horizons. The night sky, over unimaginable spans of time, will grow darker, more empty, more quiet. The brilliant tapestry of galaxies we see today may someday fade into near total blackness for those who exist far in the future. Each galaxy will become an isolated island of light, surrounded on all sides by unreachable darkness. And yet, right now, we live at a moment when the universe is still full of light, when stars still burn in staggering numbers, when galaxies still shine across cosmic distances, when the sky is alive with structure, motion, and history. This moment is fleeting in cosmic terms. From our fragile vantage point, standing on the surface of a tiny world, we are witnessing an era of extraordinary richness. We are surrounded by the visible aftermath of creation itself. The light of countless stars from every era of cosmic history continues to wash across our skies, telling us stories that began billions of years before we ever existed. Every photon that reaches your eyes tonight carries with it a fragment of deep time. It tells of nuclear fires ignited in stellar cores, of atoms formed in ancient furnaces, of gravity shaping worlds from dust, of vast journeys through expanding space, of events that may never happen again, and all of it converges here, at this one fleeting moment, on the surface of one impossibly small planet. As the scales continue to rise, something profound becomes unavoidable. The universe does not appear built for us. It is indifferent to our presence, vast beyond meaning, ancient beyond memory, silent across distances no language can capture. And yet, here we are, thinking, observing, measuring, wondering. Against this unimaginable background, even our entire solar system has already faded into near insignificance. It is now little more than a grain of structure floating within an ocean of stars. And soon, even the stars themselves will begin to fade as we retreat farther into the cosmic story. We are about to leave the realm of individual stellar neighborhoods behind. Ahead lies the scale of galaxies, then clusters, then superclusters, then the visible universe itself. And with every step, Earth shrinks further into the realm of the nearly invisible. Take a moment here to appreciate what we have covered so far. We started with Earth, a world that seems enormous from our personal experience. We saw it shrink when compared to the Sun. Then we saw the Sun shrink when compared to the distances between planets. Now, we are about to see the entire solar system shrink when compared to the distances between stars. Each step reveals a new scale of vastness, a new perspective that makes the previous one seem small. The nearest star to our Sun is called Proxima Centauri. It sits approximately 4.2 light-years away. Remember, 1 light-year equals about 5.9 trillion miles. So Proxima Centauri lies roughly 25 trillion miles from us. If you could travel at the speed of a commercial airliner, reaching Proxima Centauri would require about 5 million years. Let that sink in for a moment. 5 million years. Modern humans have only existed for about 300,000 years. Civilization has only existed for about 10,000 years. A journey to the nearest star would take longer than all of recorded human history, multiplied by 500. The fastest spacecraft humanity has launched, Voyager 1, is traveling at about 38,000 miles per hour. At that speed, it would still need over 73,000 years to reach Proxima Centauri. The distances between stars prove so enormous that they make the distances within our solar system seem almost trivial by comparison. Voyager 1, launched in 1977, is now the most distant human-made object. As of 2025, it is over 14 billion miles from Earth, well past the orbit of Pluto. It has entered interstellar space, the region between stars, but it has not escaped the Sun's gravitational influence. That extends much farther to the Oort cloud. Voyager 1 will continue traveling for thousands of years before it comes close to another star. Voyager 1 carries a golden record, a phonograph record containing sounds and images selected to represent the diversity of life and culture on Earth. This record includes greetings in 55 languages, music from different cultures and eras, natural sounds like wind and waves and animal calls, and images of humans, landscapes, and scientific diagrams. The record was intended as a message to any intelligent beings who might encounter the spacecraft in the distant future. It represents a cosmic message in a bottle drifting through the void. Proxima Centauri itself is a small red dwarf star, much smaller and dimmer than our Sun. It may have planets orbiting it, including at least one that sits within the habitable zone where liquid water could exist on a planet's surface. But we know very little about these distant worlds. Proxima Centauri is part of the Alpha Centauri system, a triple star system. The other two stars, Alpha Centauri A and B, form a binary pair orbiting each other. They are both more similar to our Sun than Proxima Centauri. If you could visit a planet in this system, you would see 2 or 3 suns in the sky, depending on your location. The night sky would look completely different from Earth's, with different constellations and the Sun reduced to just another point of light among countless others. Our Sun is just one star among hundreds of billions in our galaxy. These stars come in many different sizes. Some stars are smaller than our Sun. Red dwarfs, the most common type of star, typically measure about 10 to 50% of the Sun's diameter. But they burn their fuel very slowly and can shine for trillions of years. Red dwarfs are so common that they make up about 70 to 80% of all stars in the Milky Way, yet we cannot see any of them with the naked eye from Earth because they are too dim. Every star you see in the night sky is either more massive than the Sun or much closer than average, or both. Other stars dwarf our Sun. Blue giants and supergiants can measure 10 to several hundred times larger than the Sun. Betelgeuse, a red supergiant star in the constellation Orion, has a diameter roughly 700 times larger than the Sun. If you placed Betelgeuse at the center of our solar system, its surface would extend past the orbit of Mars. Betelgeuse is nearing the end of its life. It has exhausted most of its nuclear fuel and has swollen into a red supergiant. At some point, perhaps tomorrow, perhaps 1,000 years from now, it will explode as a supernova. When that happens, it will briefly outshine every other star in the sky except the Sun. It will be visible during daytime. For a few weeks, Earth will have a second brilliant light in the sky. Then it will fade, leaving behind a neutron star or possibly a black hole. But even the largest stars appear tiny when viewed from great distances. If you traveled just a few light years away from any star, it would shrink to a mere point of light in the sky, indistinguishable from countless others. This is a profound realization. Stars, those enormous balls of nuclear fire become invisible points at cosmic distances. The Sun, so dominant in our sky, would become just another faint star if viewed from even the nearest neighbouring star system. All that light, all that heat, all that energy, reduced to a tiny pinprick in the darkness. The stars we see in the night sky are all part of our galaxy, the Milky Way. From our position on Earth, we sit inside the Milky Way, so we see it as a band of light stretching across the sky. This band consists of billions of stars, too distant and numerous to distinguish individually. On a truly dark night, far from city lights, the Milky Way appears as a misty band arcing across the heavens. Ancient cultures saw this band and created myths to explain it. The Greeks called it Galaxies Kyklos, the Milky Circle. Many cultures described it as a river or path. Some saw it as the backbone of the night sky. The Milky Way is a spiral galaxy. It has a flat disc-like shape, with spiral arms extending from a central bulge. The galaxy measures roughly 100,000 light-years from edge to edge. Remember, a light-year equals about 5.9 trillion miles. So the Milky Way spans approximately 587,000 trillion miles across. To travel across the Milky Way at the speed of light would take 100,000 years. Light, the fastest thing in the universe, would need 100,000 years to cross from one edge of our galaxy to the other. At the speed of current spacecraft, the journey would take billions of years. The spiral arms of the Milky Way are regions of active star formation. Gas and dust concentrate in these arms, creating stellar nurseries where new stars are born. Our Sun sits in a minor arm called the Orion Spur, located between two major arms. The spiral structure rotates, but not like a solid disk. Different parts of the galaxy rotate at different speeds, creating the spiral pattern we observe. The Milky Way contains between 200 billion and 400 billion stars. Some estimates suggest even more. Along with these stars, the galaxy holds vast clouds of gas and dust, stellar nurseries where new stars form constantly. The galaxy also contains billions of planets. Recent observations suggest that most stars host at least one planet, meaning our galaxy likely contains more planets than stars. These numbers are difficult to comprehend. 200 billion is 2 followed by 11 zeros. If you counted one star per second, it would take you over 6,000 years to count all the stars in the Milky Way. And remember, each of these stars is a sun, potentially with its own family of planets, moons, asteroids, and comets. Our Sun sits about 26,000 light-years from the galactic center. We orbit the center of the galaxy at a speed of roughly 500,000 miles per hour. Even at this incredible velocity, it takes our Sun approximately 230 million years to complete one full orbit around the galactic center. The last time our Sun occupied this same position in the galaxy, dinosaurs roamed the Earth. Think about that for a moment. The Sun has orbited the galaxy about 20 times since it formed 4.6 billion years ago. Earth has existed for all those orbits, but complex life has only existed for a fraction of the most recent orbit. Humans have existed for an unimaginably brief moment in this galactic year. The center of the Milky Way holds a supermassive black hole called Sagittarius A star. This black hole contains about 4 million times the mass of our Sun, all compressed into a region smaller than Mercury's orbit. Despite its enormous mass, even this black hole occupies only a tiny fraction of the galaxy's total volume. Black holes are perhaps the strangest objects in the universe. They are regions of space where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole, called the event horizon, marks the point of no return. Anything crossing this boundary is lost forever, pulled into the singularity at the center where all known physics breaks down. The supermassive black hole at the center of the Milky Way was confirmed in 2020, when astronomers captured the first image of its shadow. This achievement required coordinating radio telescopes around the world to create an Earth-sized virtual telescope. The image shows a ring of glowing hot gas orbiting the black hole, with a dark shadow in the center where the black hole itself resides. The Milky Way also has a halo of dark matter surrounding it. Dark matter remains invisible and does not interact with light, but its gravitational effects reveal its presence. This dark matter halo extends far beyond the visible edges of the galaxy and contains several times more mass than all the visible matter in the galaxy combined. Dark matter is one of the great mysteries of modern physics. We know it exists because galaxies rotate in ways that cannot be explained by visible matter alone. The outer parts of galaxies rotate too fast. Without additional invisible mass holding them together, they should fly apart. This invisible mass, dark matter, makes up about 85% of all matter in the universe. But we do not know what it is made of. It does not interact with light or normal matter except through gravity. Detecting it directly has proven extremely difficult despite decades of effort. From our position inside the Milky Way, Earth has already become almost impossible to imagine. We are on a planet orbiting an average star, located roughly halfway out from the galactic center, in a galaxy containing hundreds of billions of stars. Finding Earth from another part of the galaxy would be like trying to locate a specific grain of sand on a beach stretching for thousands of miles. Actually, that comparison understates the difficulty. It would be more like trying to find a specific atom in a grain of sand on that beach. The number of stars in the galaxy is so large, and the spaces between them so vast, that pinpointing one particular planet orbiting one particular star would be almost impossible without knowing exactly where to look. But our galaxy is not alone. The Milky Way belongs to a small group of galaxies called the Local Group. This collection contains about 80 galaxies spread across approximately 10 million light-years of space. Most of these galaxies are small dwarf galaxies, but the Local Group also includes some large spiral galaxies. Dwarf galaxies contain anywhere from a few million to a few billion stars. Many dwarf galaxies orbit larger galaxies as satellites. The Milky Way has dozens of these satellite galaxies, including the Sagittarius dwarf elliptical galaxy, which is slowly being torn apart and absorbed by the Milky Way's gravity. The largest galaxy in the Local Group is the Andromeda galaxy, also known as Messier 31. Andromeda is a spiral galaxy similar to the Milky Way but somewhat larger. It contains roughly 1 trillion stars and spans approximately 220,000 light-years across. Andromeda sits about 2.5 million light-years away from us. Despite this enormous distance, Andromeda appears as a faint smudge in the night sky, visible to the naked eye under dark conditions. It represents the most distant object you can see without a telescope. The light you observe from Andromeda left that galaxy 2.5 million years ago, long before modern humans evolved on Earth. When you look at Andromeda, you are looking into deep time. You are seeing the galaxy as it was when our distant ancestors were just beginning to diverge from other apes. The light from those trillion stars has been traveling through space for all that time, finally reaching your eyes tonight. Any civilizations that might exist in Andromeda are seeing the Milky Way as it was 2.5 million years ago. Andromeda and the Milky Way are actually moving toward each other. In about 4 to 5 billion years, these two galaxies will collide and merge. This collision will not cause stars to crash into each other, because the distances between stars remain vast even within galaxies. Instead, the galaxies will pass through each other, gravitationally disrupting both structures before merging into a single, larger elliptical galaxy. This collision, sometimes called Andromeda-Milky Way collision or Milkomeda merger, will dramatically change the night sky. For a period of time, both galactic cores will be visible, creating spectacular views. Stars will be flung into new orbits. Some may be ejected from the merged galaxy entirely. New bursts of star formation will occur as gas clouds collide. If Earth and humanity still exist in 4 billion years, our descendants will witness one of the most dramatic cosmic events possible. The local group also contains the Triangulum galaxy, another spiral galaxy about 60,000 light-years across, and dozens of smaller satellite galaxies orbiting the Milky Way and Andromeda. These smaller galaxies include the large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches in the sky. The Magellanic Clouds are named after Ferdinand Magellan, whose expedition noticed them during the first circumnavigation of Earth in the early 1500s. To observers in the southern hemisphere, these clouds have been known since ancient times. They are irregular dwarf galaxies containing billions of stars each, and they orbit the Milky Way. But even the local group represents just one small cluster in a much larger structure. The local group belongs to the Virgo supercluster, an enormous collection of galaxy groups and clusters. The Virgo supercluster spans roughly 110 million light-years across and contains approximately 100 galaxy groups and clusters, including at least 47,000 large galaxies. At the heart of the Virgo supercluster sits the Virgo cluster, a dense collection of about 1,300 to 2,000 galaxies. This cluster lies approximately 54 million light-years from the Milky Way. The gravity of the Virgo cluster influences all the galaxies in the supercluster, causing them to slowly drift toward this massive concentration of matter. The Virgo cluster is dominated by giant elliptical galaxies, some containing trillions of stars. These galaxies, formed through mergers, the collision and absorption of smaller galaxies over billions of years. The largest galaxy in the Virgo cluster, Messier 87, contains several trillion stars. At its center lies a supermassive black hole containing billions of times the Sun's mass. In 2019, this black hole became the first one ever photographed directly, producing the now famous image of a glowing ring around a dark center. From this perspective, the Milky Way is just one galaxy among tens of thousands in our local corner of the universe. Earth, our Sun, our entire solar system, they have become almost impossible to distinguish. We exist as a tiny speck orbiting an average star in one galaxy among thousands, all bound together by gravity across tens of millions of light-years. Let this perspective settle for a moment. The Milky Way, with its hundreds of billions of stars, is just one among thousands in the Virgo supercluster. And the Virgo supercluster is just one among countless others scattered throughout space. The scale keeps expanding, each new level dwarfing the previous one. But we are not finished zooming out yet. Recent observations have revealed even larger structures in the universe. The Virgo supercluster, vast as it appears, actually forms just one small part of an even more immense structure called the Laniakea supercluster. Laniakea, whose name means immeasurable heaven in Hawaiian, spans approximately 520 million light-years across. It contains the mass of about 100,000 trillion suns and includes roughly 100,000 galaxies. The Milky Way sits near the edge of this enormous structure. Laniakea is not a random collection of galaxies. It represents a region of space where galaxies move coherently, flowing like streams toward a central gravitational basin called the Great Attractor. This region of space contains a massive concentration of matter that pulls on all the galaxies in Laniakea, including our own. The Great Attractor was discovered in the 1970s when astronomers noticed that galaxies in our region of the universe, including the Milky Way, are moving toward a particular point in space at speeds of several hundred miles per second. This motion is in addition to the expansion of the universe. Something massive is pulling on our galaxy and millions of others. The Great Attractor lies about 200 million light-years away, in the direction of the constellation Centaurus. It is partially obscured by the plane of the Milky Way, making it difficult to study. But observations suggest it contains tens of thousands of galaxies, all gravitationally bound together in enormous clusters and superclusters. The universe contains countless superclusters similar to Laniakea. These superclusters are separated by enormous voids, regions of space that contain very few galaxies. These cosmic voids can span hundreds of millions of light-years across. They represent the emptiest places in the universe, containing almost nothing but dark matter and occasional small galaxies. If you could travel through a cosmic void, you would see almost no galaxies in any direction. The nearest ones would be so far away that they would appear as faint smudges even through powerful telescopes. You would be surrounded by darkness, more profound and complete than anything experienced in the densely populated regions near galaxy clusters. The superclusters and voids form a cosmic web, a large-scale structure that looks somewhat like soap bubbles or a sponge. The superclusters form the dense walls and filaments, while the voids represent the empty spaces between. This pattern extends as far as we can observe in every direction. This cosmic web is the result of how matter has distributed itself under gravity over billions of years. In the early universe, matter was distributed almost uniformly, with only tiny variations in density. Over time, gravity amplified these small differences. Denser regions attracted more matter, becoming even denser. Less dense regions lost matter to surrounding areas, becoming voids. The result is the complex structure we see today. The largest structures in the universe are galaxy filaments and walls. The Sloan Great Wall, discovered in 2003, stretches approximately 1.3 billion light-years across. The Hercules Corona Borealis Great Wall, identified in 2013, may span up to 10 billion light-years, though its exact size remains debated among astronomers. These structures represent the largest known objects in the universe. Nothing appears to be organized on a larger scale. Beyond this level, the universe begins to look relatively uniform in all directions. This uniformity holds great significance for our understanding of the cosmos. These walls and filaments contain thousands of galaxies, each containing billions or trillions of stars, each star potentially hosting planets. The number of worlds contained in just one of these structures is beyond human comprehension, and there are many such structures throughout the observable universe. At the largest scales, when you examine volumes of space, billions of light-years across, the universe appears roughly the same everywhere. Galaxies distribute themselves relatively evenly. There is no center, no edge, no special direction. This property, called cosmological homogeneity, suggests that the universe has no preferred location. Our view from the Milky Way would look essentially the same if we observed from any other galaxy billions of light-years away. This principle, sometimes called the cosmological principle, has profound implications. It means that the laws of physics are the same everywhere in the universe. It means that our observations here on Earth can tell us about the entire cosmos. It means that we are not in any special location, that the universe looks basically the same from every vantage point. This brings us to the concept of the observable universe. The observable universe represents the portion of space from which light has had time to reach us since the universe began. The universe started approximately 13.8 billion years ago in an event we call the Big Bang. Since then, light has traveled outward in all directions, but the universe has also been expanding during this time. This expansion means that galaxies we observe are now much farther away than they were when their light first began its journey toward us. The most distant objects we can observe lie approximately 46.5 billion light-years away from us right now. This distance defines the radius of the observable universe. The full diameter of the observable universe measures approximately 93 billion light-years. This represents the largest distance we can ever hope to see. Anything beyond this horizon remains forever invisible to us because its light has not had sufficient time to reach Earth. This concept is difficult to grasp. If the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? The answer lies in the expansion of space itself. While the light was traveling toward us, space was stretching, carrying the source of that light even farther away. By the time the light reaches us, the object that emitted it is much farther than 13.8 billion light-years away. Space itself is expanding. This does not mean galaxies are moving through space. It means space between galaxies is growing. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they are traveling across the rubber, but because the rubber itself is stretching. This is similar to how the universe expands. The observable universe contains at least 2 trillion galaxies. That number comes from recent deep field observations made by the Hubble Space Telescope and other instruments. Each of these galaxies contains millions or billions or even trillions of stars. And most of these stars likely host planetary systems. 2 trillion galaxies. Try to imagine that number. If you counted one galaxy per second, it would take you over 63,000 years to count them all. And each galaxy contains billions of stars. The total number of stars becomes almost meaningless because our brains cannot process numbers that large in any meaningful way. The total number of stars in the observable universe is estimated to be around 1 septillion. That number is 1 followed by 24 zeros. To write it out, 1 septillion equals 1 million trillion stars. If every star in the observable universe represented a single grain of sand, you could fill all the beaches on Earth many times over and still have sand left over. Actually, that comparison understates it dramatically. The number of stars in the observable universe exceeds the number of grains of sand on all of Earth's beaches by a factor of about 10. There are more stars in the universe than grains of sand on Earth. That fact alone should fundamentally change how you think about cosmic scales. Now, let us place Earth back into this cosmic context. Earth, with its diameter of roughly 8,000 miles, orbits an average star that is one among hundreds of billions in the Milky Way galaxy. The Milky Way is one galaxy among tens of thousands in our local supercluster. Our supercluster is one among millions scattered throughout the observable universe. And the observable universe itself may represent only a tiny fraction of the total universe, which could extend infinitely in all directions. If you wanted to build a scale model of the observable universe and made it small enough to fit inside a sphere 100 feet across, Earth would be far smaller than an atom. In fact, Earth would be smaller than a proton, smaller than a quark, smaller than anything we have names for. It would be, for all practical purposes, completely invisible and utterly insignificant in size. Let me try to put this in yet another way. If the observable universe were the size of Earth, the Milky Way galaxy would be about the width of a human hair. And Earth, in that model, would be about 1/1,000,000th the size of a single atom. It would be so small that no measuring instrument could possibly detect it. It would be, quite literally, infinitesimal. This represents the true scale of the universe. Earth is not just small, it is so phenomenally tiny that it barely registers when compared to cosmic dimensions. Every mountain range that seems so permanent, every ocean that appears so vast, every continent that stretches for thousands of miles, all of it exists on a world that would be invisible in a scale model of the universe. And yet, despite this cosmic insignificance in terms of size, something remarkable exists on this tiny world. Something that, as far as we know, may be extraordinarily rare or even unique in the universe. But before we lose ourselves entirely in the vastness of space, we need to pause and consider what all of this truly means. Because size alone does not tell the complete story. Something remarkable happened on this tiny world, something that, as far as we know, may be extraordinarily rare in the universe. Earth is not just a planet, it is a living world. Our planet teems with life in almost every environment. Life thrives in the deepest oceans, on the highest mountains, in frozen polar regions, in scorching deserts, even deep underground in solid rock. Life on Earth displays incredible diversity. Scientists have identified approximately 8.7 million species, though the actual number might be much higher. These species range from microscopic bacteria to enormous blue whales measuring over 100 feet long. Consider the range of life on Earth. Single-celled organisms have existed for over 3 billion years. They live in every environment, from boiling hot springs to frozen Antarctic rocks to the human digestive system. Plants, which emerged about 450 million years ago, transformed Earth's atmosphere and created the oxygen-rich air we breathe. Animals, in their stunning diversity, occupy every ecological niche imaginable. Some organisms live in extreme environments that would kill most other life forms. Bacteria have been found living in nuclear waste, in acidic hot springs, in rocks miles underground, even in the stratosphere. Tardigrades, microscopic animals, can survive in the vacuum of space, endure temperatures near absolute zero, and withstand radiation levels that would kill almost any other organism. Life, once established, proves remarkably resilient and adaptable. The existence of life makes Earth special. We know of no other place in the universe where life certainly exists. We have found no evidence of life on Mars, though we continue searching. We have detected no signals from alien civilizations despite decades of listening with radio telescopes. We have discovered thousands of planets orbiting other stars, and some appear to orbit in the habitable zone where conditions might allow liquid water, but we have no proof that any of these worlds actually host life. The search for extraterrestrial life has intensified in recent decades. Missions to Mars seek signs of past or present microbial life. Future missions will explore the ice-covered moons Europa and Enceladus, which have liquid water oceans beneath their surfaces. The James Webb Space Telescope is analysing the atmospheres of exoplanets, looking for chemical signatures that might indicate biological activity, but so far we have found nothing. Earth remains the only world we know with certainty hosts life. This could mean that life is extremely rare, requiring such specific conditions that it emerges only on a tiny fraction of planets. Or it could mean that life is common, but we simply have not looked carefully enough or in the right places yet. This absence of evidence does not mean life exists only on Earth. The universe is vast beyond comprehension. Even if life is rare, the sheer number of planets and stars suggests that other living worlds probably exist somewhere. But the distances between stars are so enormous that we may never detect life elsewhere, even if it is relatively common. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative civilizations in the Milky Way galaxy. It considers factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and the fraction that develop intelligent life. Depending on the values you assign to these uncertain factors, the equation suggests anywhere from 0 to millions of civilizations in our galaxy alone. The Fermi paradox asks a troubling question. If intelligent life is common in the universe, where is everyone? Why have we detected no signals, no probes, no evidence of other civilizations? Various solutions have been proposed. Perhaps technological civilizations are short-lived, destroying themselves soon after developing. Perhaps interstellar travel is simply too difficult. Perhaps we are looking in the wrong ways or at the wrong times. Or perhaps we really are alone, or at least one of the first civilizations to emerge. The question of whether we are alone remains one of the most profound mysteries we face. If life exists only on Earth, or if it is extraordinarily rare, then every living thing on our planet becomes precious beyond measure. Each species represents a unique experiment in survival and adaptation. Each organism carries genetic information that took millions or billions of years to develop. If intelligent life is even rarer than simple life, then human consciousness takes on cosmic significance. We are, as far as we know, the only beings in the observable universe capable of understanding the universe itself. Through science and observation, through mathematics and reason, we have figured out where we are and what surrounds us. We have determined that those points of light in the night sky are actually distant suns. We have calculated the distances to these stars and measured the sizes of galaxies. We have traced the history of the universe back to its beginning and predicted its ultimate fate. Consider what we have achieved in just a few centuries of serious scientific inquiry. We have determined that Earth orbits the Sun. We have discovered that the Sun is one star among hundreds of billions in a galaxy. We have found that our galaxy is one of trillions. We have measured the age of the universe. We have detected gravitational waves from colliding black holes billions of light years away. We have photographed the shadow of a black hole. We have sent probes to every planet in our solar system and beyond. This ability to comprehend the cosmos represents something truly extraordinary. Matter, following blind physical laws, has organized itself into complex structures capable of awareness, capable of thought, capable of asking questions about existence itself. The atoms in your body were forged inside stars that died billions of years ago. These atoms drifted through space, eventually gathering into a new solar system, forming a planet and assembling themselves into living organisms. And now, through you, these atoms have become aware of their own history and their place in the universe. This is perhaps the most astounding fact in all of science. The universe has produced structures, us, capable of understanding the universe. Through billions of years of cosmic evolution, from the Big Bang to the present, matter has organized itself in increasingly complex ways. First atoms, then molecules, then simple organic compounds, then self-replicating molecules, then cells, then multicellular organisms, then nervous systems, then brains, then consciousness, then self-awareness, then science. This emergence of consciousness may be the rarest phenomenon in all of nature. Galaxies form through simple gravitational forces. Stars ignite through nuclear fusion. Planets coalesce from disks of dust and gas. All of these processes follow predictable physical laws. But consciousness, the ability to experience, to think, to understand, this seems to require an extraordinary sequence of conditions that may be vanishingly rare. If consciousness is indeed rare, then its loss anywhere in the universe represents a tragedy of cosmic proportions. Every time a species goes extinct on Earth, the universe loses a unique form of life that may never evolve again. Every potential future where humanity fails to survive means the silencing of the universe's ability to know itself in this region of space. Earth has experienced 5 major mass extinctions in its history. The most severe, the Permian extinction 252 million years ago, wiped out about 96% of all marine species and 70% of terrestrial species. Life recovered, but it took millions of years. The most recent major extinction, 66 million years ago, ended the age of dinosaurs and paved the way for mammals to diversify. Now, some scientists argue we are in the midst of a 6th mass extinction, this one caused by human activity. Species are going extinct at rates hundreds or thousands of times higher than the natural background rate. Habitat destruction, pollution, climate change, and direct hunting are driving countless species toward extinction. Each one that disappears represents millions of years of evolution, a unique solution to the challenge of survival, gone forever. If intelligence is rare in the universe, this loss takes on even greater significance. This perspective should fundamentally change how we view our responsibilities. The conflicts between nations, the competition for resources, the environmental destruction we cause, all of these issues take on different character when we remember our cosmic context. We are not fighting over a vast territory. We are fighting over different regions of a dust speck. We are not competing for the resources of an enormous world. We are competing for the resources of something almost too small to measure against the scale of the universe. Consider how an intelligent observer from another galaxy might view us. If they could somehow look back at Earth across millions of light years, they would see a tiny planet orbiting an unremarkable star. They would see a world covered with life, an incredibly rare phenomenon, and if they could observe closely enough, they would see one species on that world, humans, who have developed technology and science, who have begun to understand the cosmos, who have even sent probes beyond their own planet. Would this hypothetical observer understand our divisions and conflicts? Would they comprehend why we fight wars over territory or resources when we all share the same tiny world? Or would they find it incomprehensible that a species capable of understanding the universe spends so much effort competing against itself rather than working together to preserve and expand life? These questions have no easy answers. Human nature includes cooperation and conflict, creation and destruction. We have accomplished remarkable things as a species. We have developed art, music, literature, philosophy, mathematics, and science. We have sent humans to the moon and robots to Mars. We have built the Large Hadron Collider and the James Webb Space Telescope. We have decoded our own genome and begun to understand the fundamental particles that make up matter. The Large Hadron Collider, the world's largest particle accelerator, lies in a tunnel 17 miles in circumference beneath the border of France and Switzerland. It accelerates particles to 99.9999% to the speed of light and smashes them together, recreating conditions similar to those just after the Big Bang. Through these experiments, physicists confirm the existence of the Higgs boson in 2012, a particle that helps explain why other particles have mass. The James Webb Space Telescope, launched in 2021, orbits the Sun about 1 million miles from Earth. It observes the universe in infrared light, allowing it to see through dust clouds and detect the heat signatures of distant objects. It has captured images of galaxies as they existed over 13 billion years ago, showing us the universe when it was young. It has analysed the atmospheres of exoplanets and revealed the composition of distant nebulae in stunning detail. But we have also created weapons capable of destroying civilization. We have pushed species to extinction and damaged ecosystems. We have polluted the air, the water, and the land. We face challenges like climate change that threaten to alter Earth's environment in ways that could harm billions of people. The concentration of carbon dioxide in Earth's atmosphere has increased by about 50% since the Industrial Revolution began. This increase has caused global average temperatures to rise by about 1.1 degrees Celsius. This may not sound like much, but it is causing ice caps to melt, sea levels to rise, weather patterns to shift, and ecosystems to change faster than many species can adapt. If current trends continue, the consequences could be severe. Looking far ahead into the future, beyond Earth's eventual fate, we can ask what humanity's ultimate potential might become. If we survive the next few centuries, if we learn to live sustainably on our small planet or spread to other worlds, what might we evolve into over millions or billions of years? The universe will remain hospitable to life for an incredibly long time. Stars will continue burning for trillions of years. Planets will keep orbiting these stars. The physical laws that allow complex structures to exist will remain in force. If humanity or its descendants survive and spread beyond Earth, we could potentially outlive not just our planet, but our Sun, our galaxy's current form, perhaps even the current era of star formation in the universe. Our Sun will remain stable for another 5 billion years. That is longer than Earth has existed so far. In that vast span of time, if we survive, we could accomplish things we currently cannot imagine. We could spread throughout the solar system, terraforming Mars, building habitats in the asteroid belt, establishing colonies on the moons of Jupiter and Saturn. Our descendants might spread throughout the Milky Way, establishing civilizations on thousands or millions of worlds. They might develop technologies we cannot currently imagine, technologies that make interstellar travel practical or routine. They might transform themselves, merging with artificial intelligence or adopting new forms better suited for life in space or extreme environments. They might engage in cosmic engineering projects, moving stars, building megastructures, even creating new habitable worlds. They might seed the galaxy with life, taking Earth's biosphere and replicating it on countless other planets. Or they might encounter other intelligent species and join a galactic community we currently know nothing about. Some physicists and futurists speculate about truly advanced civilizations, those that have been developing for millions or billions of years. Such civilizations might have capabilities that seem like magic to us. They might harness the total energy output of stars using structures called Dyson spheres. They might manipulate space-time itself, creating wormholes for faster-than-light travel. They might upload their consciousness into machines or energy fields, transcending biological limitations entirely. But these potential futures remain just that, potential. Civilizations might prove to be fragile things, brief sparks of consciousness that appear and vanish on cosmic timescales. We might destroy ourselves through warfare, through environmental collapse, through dangerous technologies we develop faster than the wisdom to use them safely. Earth might return to a simpler biosphere, or even become lifeless, and the universe would continue on, vast and indifferent to our fate. The choice, to the extent we possess one, belongs to us. Our individual lives are brief, yes, Our planet is tiny, yes, but the cumulative effect of billions of humans making choices, developing knowledge, creating technology, and passing this knowledge to the next generation has brought us to a critical moment in our history. We are the first species on Earth capable of truly comprehending the cosmos. We are also the first capable of either spreading life beyond our planet or potentially extinguishing it entirely here. No other species has ever faced this responsibility. No other species has ever possessed this capability. The decisions we make in the coming decades and centuries will determine whether Earth's experiment with intelligent life succeeds or fails. Will we learn to live sustainably on our small world? Will we overcome our divisions and work together to address global challenges? Will we develop the technologies needed to become a multi-planet species? Will we preserve Earth's biosphere and protect the countless other species that share our world? These questions remain open. The future has not been written, but the potential exists for humanity to become something far greater than we are today. The potential exists for Earth's story to continue for billions of years, for life and consciousness to spread from our tiny world to countless others, for the universe to awaken more fully to its own existence through the eyes of our descendants. We have covered enormous ground tonight. We began with Earth and zoomed outward, comparing our planet to progressively larger structures until we reached the observable universe itself. Along this journey, we discovered something profound and perhaps unsettling. Earth is small, smaller than most people ever truly comprehend. When you place it alongside stars, galaxies, and cosmic structures, Earth becomes so tiny that it almost vanishes from view entirely. Let us retrace this journey briefly. We started on Earth, a world that seems vast from our everyday experience. We saw how large it is in human terms, how long it would take to walk around it, how many square miles cover its surface. Then we looked at the moon, and Earth stopped being everything. We saw the vast empty space between Earth and its nearest neighbor. Then we looked at the sun, and Earth shrank to a tiny fraction of its volume. We saw how the sun dominates the solar system, containing almost all of its mass. Then we looked at the distances between planets, and the sun shrank to a point. We saw the vast gulfs of empty space in our own solar system. Then we looked at the nearest stars, and our entire solar system shrank to insignificance. We saw how the distances between stars dwarf the distances between planets. Then we looked at the Milky Way galaxy, and our sun became one of hundreds of billions of stars, impossible to distinguish from countless others. Then we looked at galaxy clusters and superclusters, and the Milky Way became one galaxy among thousands. We saw structures hundreds of millions of light years across. Finally, we looked at the observable universe, and even these vast structures became mere details in an incomprehensibly large cosmos. If you constructed a scale model of the observable universe, Earth would register smaller than an atom. It would measure smaller than anything you could possibly see or measure with any instrument. It would be, for all practical purposes, entirely non-existent in terms of size. But Earth is also home. Every human who has ever lived was born here. Every thought that has ever been thought, every emotion that has ever been felt, every achievement that has ever been accomplished, all of it happened on this small planet. Earth might be tiny when measured in cosmic terms, but it represents everything to us and to every other living thing that calls it home. Think about everything that has happened on Earth. Every person you have ever known lived on this planet. Every book ever written was written here. Every piece of music ever composed was composed here. Every discovery, every invention, every moment of love and joy and sorrow, all of it on this tiny world. Earth is the stage for all of human drama, all of human history, all of human achievement and failure. And here is the truly remarkable part. We can understand this. We can comprehend, at least intellectually, just how small we are in the grand scheme of the universe. We can observe the cosmos and grasp its immense scale, even though doing so requires us to think in ways that feel completely unnatural. That ability represents something extraordinary. That capacity marks us as special. No other species on Earth can do this. No other organism can look up at the stars and understand what they are seeing. No other form of life can measure distances in light years or comprehend the age of the universe. Only humans, and perhaps other intelligent species elsewhere in the cosmos, possess this capability. Out of all the planets orbiting all the stars in all the galaxies across the observable universe, Earth is the one world that we know with certainty has produced beings capable of understanding the cosmos. We might not be alone in this achievement. There might be countless other civilizations scattered across the universe, looking up at their own night skies and contemplating their place in the vastness, but we do not know this for certain. Right now, based on everything we have observed and discovered, Earth remains the only place we know where conscious, intelligent life exists. That fact makes Earth precious beyond any measure of value. Size does not determine worth or significance. What matters is what exists here, what has emerged on this world, and what has emerged here on this tiny planet is something truly remarkable. Life in all its diversity and complexity. Consciousness, the ability to experience and to be aware. The capacity to wonder, to question, to seek understanding of the universe we inhabit. So yes, Earth is remarkably small when measured against the cosmos. But Earth is also irreplaceable, at least to us. It is the only home we have ever known. It is the only home any human has ever known. And in a universe that is vast, mostly empty, and apparently mostly lifeless, a small world abundant with life becomes something to treasure and protect. Carl Sagan, the astronomer and science communicator, once described Earth as a pale blue dot. In 1990, at his suggestion, Voyager 1 turned its camera back toward Earth from a distance of about 3.7 billion miles. The resulting image showed Earth as a tiny speck, less than 1 pixel in size, suspended in a beam of scattered sunlight. Sagan wrote that this image emphasizes our responsibility to deal more kindly with one another and to preserve this pale blue dot, the only home we have ever known. The next time you step outside on a clear night and look up at the sky, remember what you have learned tonight. The stars scattered across the darkness are part of the Milky Way, our home galaxy. Those stars are actually suns, many of them likely surrounded by their own families of planets. And our galaxy, vast as it seems, is just one of trillions scattered throughout an almost unimaginably enormous cosmos. Earth is tiny when placed in all that vastness, smaller than we can truly comprehend. But Earth is also home, and that simple fact matters more than size could ever matter. This is where we evolved. This is where we live. This is where all of human history has unfolded. This is the world we must protect and preserve, not just for ourselves, but for all the life that shares it with us. Thank you for joining me on this journey across the cosmos tonight. If you found this exploration meaningful, if it changed your perspective or made you think differently about our place in the universe, please consider supporting this channel with a like or a subscription. Your support genuinely helps me continue creating these deep explorations of space and our place within it. And remember, you are standing right now on a planet that is tiny beyond comprehension when compared to the vastness of the universe. But you are also standing on the only world we know with certainty that hosts life, consciousness, wonder, and the ability to ask questions about existence. That makes this tiny world special. That makes you special. that is something worth celebrating. Sleep well tonight, knowing that you are part of something vast and beautiful. The universe is enormous beyond imagination. Earth is tiny beyond measure. But Earth is precious. Earth is home. And you, living on this small world, experiencing this moment, are part of its ongoing story. You are made of atoms, forged in the hearts of dying stars, arranged in patterns complex enough to contemplate the universe itself. In you, the universe has become aware of itself, if only briefly, if only in this one small corner of space. That awareness is a gift, that understanding is a privilege, that consciousness is a responsibility. We are the universe's way of knowing itself. We are the method by which matter has become aware of matter. We are, perhaps, the cosmos coming awake. Carry this perspective with you. Let it inform how you live, how you treat others, how you view our shared home. We are all passengers on this tiny world, hurtling through the vastness of space at hundreds of thousands of miles per hour, orbiting a star that is itself orbiting the center of a galaxy that is moving through space as part of a cosmic dance of unimaginable scale. And yet, here we are, conscious, aware, thinking, wondering. That is the true miracle. Not the size of the universe, but the fact that the universe has produced beings capable of understanding it. Not the vastness of space, but the emergence of consciousness in the midst of that vastness. You matter. Your life matters. Your experiences matter. Not because you are large, but because you are aware. Not because you occupy significant space, but because you can comprehend space. Not because you are at the center of the universe, but because you can understand that there is no center, that we are all equally insignificant and equally precious. Good night.